Welcome back to Collapsed Latents. This week in AI, where we cut through the noise and bring you the most groundbreaking advances in artificial intelligence, distilled into one electrifying episode. This week, we're diving into 5 revolutionary papers that aren't just pushing the envelope, they're redefining the envelope. From trillion-parameter scientific supermodels to AI that thinks with pixels, from OCR that reconstructs documents like inverse rendering, to video models that learn to align with human taste in real time. This is AI at its most ambitious, intelligent, and transformative. Let's jump in. #1. Intern S1 Pro, the scientific supermodel that outsmarts specialists. Imagine a single AI that can predict protein folding, analyze MRI scans, simulate climate systems, and write a research paper, all in one breath. Meet Intern S1 Pro, the first trillion-parameter scientific multimodal foundation model. And it's not just bigger. It's smarter. At 1 trillion parameters, it's the largest open-source scientific model ever built. But the real magic? It's a specializable generalist, a model that masters over 100 scientific tasks across chemistry, materials science, life sciences, and earth sciences, without sacrificing general intelligence. How? Through SAGE, synergistic architecture for generalizable experts. The foundation layer is trained on 6 trillion tokens of scientific and general data. The fusion layer merges general reasoning with domain-specific expertise via joint training. The evolution layer uses agentic reinforcement learning to self-improve, planning, reasoning, and refining its own logic. And it's not just theory. It beats proprietary giants. On SciReasoner 10 scientific disciplines, 55.5 far ahead of Gemini-3-Pro 14.7 and GPT-5.2 13.6. On chemistry, small instruct 74.8. On materials science, MatBench 72.8. On biological microscopy, MicroVQA 63.3. Even in agent benchmarks, where real-world planning matters, ScreenSpot V2 93.6, the highest score ever. But here's the kicker. Intern S1 Pro outperformed a specialized biology model, biology instruction, on protein fluorescence and function prediction. Same data, same tasks, but the generalist understood better. Why? Because larger models with strong reasoning don't just memorize, they infer. And it's all powered by grouped routing, solves expert load imbalance and straight-through estimators, fixes gradient sparsity, making training stable at trillion scale. This isn't a tool. It's a collaborator. And it's open source. The future of AI for science. It's already here. #2. TerraScope, where AI doesn't just see, it reasons with pixels. Now imagine you're analyzing a satellite image of a coastal region. Rivers, farmland, cities, forests. You ask, what percentage of this image is water? A standard vision language model. It'll guess. It'll hallucinate. It'll give you a number with no proof. Enter TerraScope, a breakthrough framework that forces AI to think with pixels. Unlike models that treat images as text or captions, TerraScope interleaves language reasoning with pixel-accurate segmentation masks. Every time the model says, "I'm identifying water areas," it generates a mask. That mask is used to extract real visual tokens, which are fed back into the reasoning process. This creates a closed loop of visual grounding. The model sees, reasons, grounds, and repeats. Built on a dual decoder architecture, TerraScope uses one decoder for language, one for segmentation. When it hits the special token, the mask decoder activates, producing a precise region, which is then used to inform the next step. And it's not just for optical images. It fuses optical and SAR, radar, data, switching automatically based on cloud cover, surface conditions, or lighting. All powered by TerraCoT, a 1 million sample dataset with full chain-of-thought reasoning and pixel-level masks. Evaluated on TerraScope Bench, the first benchmark for pixel-grounded geospatial reasoning, it achieves 68.9% accuracy, compared to 43.3% for the next best model. Even more telling, the correlation between segmentation quality, IOU, and answer accuracy is R equals 0.607, meaning better visual grounding leads to better reasoning. Real example. Standard models, about 30%, no evidence. TerraScope, I identify water areas. 8,490 pixels, out of 65,536. That's 13%, with a near-perfect mask. This isn't just better accuracy. It's trust. For disaster response, climate monitoring, urban planning, when lives and decisions depend on data you don't want to guess. You want a proof. TerraScope delivers that, with just 2.8% extra parameters and competitive inference speed. This is the future of Earth observation, not black box AI, but co-pilots with transparent minds. #3. MinerU-Diffusion, OCR that reconstructs documents like inverse rendering. Now think about scanning a document, say, a research paper with tables, formulas, and complex layouts. Traditional OCR. It generates text one token at a time, left to right. But here's the flaw. Document content is deterministic. A sentence doesn't change based on what came before it. Yet autoregressive models treat every word as a probabilistic guess, relying on language priors, not visual reality. When the image is noisy or low-res, they hallucinate, and errors cascade. Enter MinerU-Diffusion, a radical rethink of OCR as inverse rendering under visual conditioning. Instead of autoregressive decoding, it uses diffusion-based parallel decoding, reconstructing the full text sequence from visual evidence in parallel. It models the posterior as PYX equals letter 1D47 letter 1D2 EP, Y left paren letter 1D47 right paren, Y letter 1D47 right paren, X. But within each block, tokens are updated simultaneously, thanks to a block attention mechanism that scales near linearly, not quadratically. This means thousands of tokens, entire papers, can be processed fast and accurately. And to stabilize training, a two-stage curriculum. Stage I, train on 7.5 million diverse documents to build strong visual semantic alignment. Stage II, identify uncertain cases via inference consistency, refine with human-AI collaboration, and fine-tune with adaptive weighting. The results? On OmniDoc Bench V15, 93.37 overall score, competitive with top autoregressive models, but 2 times faster decoding. And in the semantic shuffle benchmark, where words are randomly shuffled but the layout stays the same, autoregressive models collapse. MinerU-Diffusion. It holds steady. Because it's not guessing. It's reconstructing what's actually there. This isn't just faster. It's more honest. It's OCR as inverse rendering, where the image is the output and the text is the input. And the code. Open on GitHub. The future of document understanding is here. #4. Astrolabe, reinforcement learning that makes video models feel human. Now imagine generating cinematic quality videos in real time, smooth, coherent, perfectly aligned with your creative intent, without waiting minutes per frame. Enter Astrolabe, a breakthrough framework that finally aligns distilled autoregressive video models with human preference. Why does this matter? Because while autoregressive models enable streaming and low latency, they often produce jittery motion, artifacts, and unnatural dynamics. Why? Because distillation, compressing a powerful bidirectional teacher into a lean student, preserves distribution, not aesthetic quality. Traditional RL. It requires storing full sampling trajectories, killing efficiency for streaming. Astrolabe flips the script, forward process RL. It uses negative-aware fine-tuning. Compare a clean sample and a noisy version, then define implicit positive-negative policies via interpolation. No trajectory storage. No solver coupling. And for long videos, a streaming training scheme with a rolling KV cache, a fixed-size frame sync for global context, and a rolling buffer for local conditioning. Memory stays constant, no OOM crashes. Plus, group-wise sampling, one prefix, multiple candidate clips decoded in parallel, reducing rollout overhead dramatically. To prevent reward hacking, it uses a multi-reward objective. Visual quality, HPSV3, motion dynamics, video align, and text video alignment, RGB video align. And a selective KL penalty. Only high uncertainty samples where reward models disagree get penalized. Clean samples are free to explore. The results? +13 HPSV3, +01 motion quality, without slowing inference. 30-second coherent generations from models trained on just 5-second clips. In narrative long generation, smoother transitions, better detail retention. Ablations confirm, remove the streaming scheme. OOM. Skip selective KL. Reward hacking. Drop multi-reward. Motion collapses. Astrolabe proves that local advantage guidance plus selective regularization can stabilize online RL in streaming settings. This isn't just better video. It's human-aligned, efficient, and scalable. The future of real-time video generation. It's not just fast. It's feeling right. #5. The hidden cost of self-distillation, when confidence kills reasoning. Finally, let's talk about a paradox that's been haunting AI reasoning. Self-distillation sometimes makes models worse. Yes, training a model to imitate itself can degrade performance. Especially in math. Why? Because self-distillation suppresses epistemic verbalization, those let me check moments. These aren't filler. They're signals of uncertainty. The model questioning its path, holding multiple hypotheses, adjusting beliefs. But when the teacher has access to the correct solution, it generates short, confident, error-free reasoning, no hesitations. The student imitates that style. But at inference time, no solution, no hints, just a model trained to be too sure. It commits early, can't backtrack, fails on novel problems. We tested this. On DAPO Math 17K, self-distillation SDPO dropped accuracy by up to 40%. Despite shorter, more confident responses. Why? Because as task coverage grows, epistemic verbalization becomes essential. In small, repetitive datasets like chemistry, self-distillation shines. But in diverse, open-ended domains like math, it collapses. We quantified it with conditional mutual information. As the teacher's context reduces uncertainty, epistemic tokens plummet, and OOD performance crashes. One model lost 70% of its epistemic tokens. Its AIME24 accuracy dropped from 54.7 to 20.2. Even disabling thinking mode. The same pattern. Because confidence still leaks from teacher to student. So what's the fix? reward not just correctness, but uncertainty awareness. We need post-training objectives that preserve the process of reasoning, not just the answer. Because real intelligence isn't about knowing the answer. It's about knowing when you don't know, and being able to adjust. Self-distillation isn't evil, but it's not a universal solution. And the lesson: don't train models to be confident. Train them to be reflective. This week we've seen a powerful pattern. The future of AI isn't just about scale or speed. It's about alignment. Intern S1 Pro aligns science with generalization. TerraScope aligns vision with pixel-level truth. MinerU-Diffusion aligns OCR with visual reality. Astrolabe aligns video with human taste. And the self-distillation insight. It teaches us that true reasoning requires humility, not just confidence. These aren't just incremental updates. They're paradigm shifts, where AI stops mimicking humans and starts thinking like them. So if you're a researcher, developer, or just an AI enthusiast, this is your moment. The tools are open. The ideas are clear. The future is collaborative. Like this video. Subscribe to Collapsed Latents, where we keep you ahead of the curve. Drop a comment, which of these breakthroughs excites you most. And stay curious. The next wave is already building.